And we're back, but now with weak bases instead of weak acids. The good news is that we are going to be using all of the same rules and all of the same processes that we used with acids, and so we're not actually doing anything different in that sense. The slightly bad news is that it is a different reaction, so we are learning a new reaction here. But that is, again, just slightly, because like I said, practically everything is identical. Really the only thing that's different is just the generalized equation here. We still are just going to have one reactant show up in the equilibrium process, and we'll have two products. I don't know why I'm missing the AQ there, but anyway, we'll have two products, one reactant, just like we did with the acid. But now we're going to have OH minus instead of H plus, and we'll have the base and the conjugate acid instead of the acid and conjugate base. So it is very, very similar, and we're going to use all the same processes. It's just going to be for a base instead of an acid. So we have an example of that here, where we have a weak base, which would be ammonia in this case, and it reacts with water to produce the conjugate acid ammonium, and OH minus, the conjugate base. Like I said, the equilibrium expression is practically identical to that for the acid. We're just going to plug in base stuff instead of acid stuff. So instead of having an acid on the bottom, we have the base. Instead of having the conjugate base on top, we have the conjugate acid. And instead of H plus, we have OH minus. But other than, just plugging in base stuff instead of acid stuff, it's the exact same equilibrium. The algebra is not going to be any more difficult for bases than it was for acids. And just like with acids, we have our own special dissociation constant here. Instead of Ka, which was for acids, for bases we have Kb for bases, because we are super original in how we name things, which I'm kind of making fun of it, but in a way it's actually really nice. You don't want someone just coming up with random letters because they felt like it, and then everyone's just wondering why was this letter picked. It's not super original, but at least it's clear that it's Kb, B for base. So here we have a few different dissociation constants for a few different random weak bases. Some of these you might have seen before, like ammonia, we've seen a few times already. Carbonate ion, you might have heard of aniline or pyridine. You possibly have heard of those. So these are just a few random weak bases. But let's go ahead and work through a weak base problem, just to show you that it really is no different than a weak acid problem, with the one possible exception being that if the goal of the problem is to find the pH, we will have one extra step at the end, because when you work through the equilibrium step here, you usually find the concentration of OH minus, and so we have to do one extra step there to convert that into H plus so that we can find the pH. But in this case, we actually aren't asked to find the pH. We're just finding the concentration of hydroxide. So we're told that we have 0.25 molar trimethylamine, which is a weak base. We're given Kb, but we're not given any equilibrium concentrations, so that means we're going to be using X here. We're going to have an unknown on our ICE table. So let's go ahead and complete our ICE table here. So just like with the acid, we will have 3 parts. We'll have our base, we'll have OH minus, and we will have our conjugate acid. Now in the question, we're told we're starting with 0.25 of the base. We're not given any information about these, and so we're going to assume we have none of those. Because we're not given enough information to have any equilibrium concentrations, we're just going to go ahead and plug in our X values here. So we're going to lose some amount X of B, and we're going to gain some amount x of these two, which means we'll have x and x for our equilibrium concentrations of OH minus and the conjugate base. And then we will have 0.25 minus x for the equilibrium concentration of B. Now I'm going to make the x a small assumption here because there is 4 orders of magnitude difference between Kb and the concentration of the base. I will double check it just to make sure that it's fine, but it's going to be fine. I can tell you that now, but like I said, I will just double check just to put your mind at ease. So I now have all of my equilibrium concentrations ready to plug into the equilibrium expression, even though I don't know what any of them are yet. So Kb is equal to 6.3 times 10 to the negative 5, which is equal to x squared. And actually, should have had the square outside the parentheses, but oh well, doesn't change the math. Whoa, why did it do that? That was weird. Over 0.25 minus x. So, like I said, I'm going to make the x a small assumption, so I'm just going to say, you're not there. La 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 la, I don't see you. I can't hear you. So, no x anymore there, so then that makes the algebra much easier. So we're going to have, let's see, 6.3 times 10 to the negative 5 times 0.25, and then take the square root of that. And x is 0.00. Oh, let's see, I get only 2 sig figs, so that'd be 4.0, I guess. Yeah. So that is the concentration of OH minus. Now, if the question did actually ask us to find the pH, which, yeah, so we don't have another one there that does that, it would be a pretty simple process to do that. So just to show you, you actually have 2 different possibilities. You could go this route. So we know that the concentration of OH minus times the concentration of H plus gives you, or is equal to 1 times 10 to the negative 14. So you could plug this in there and solve for H plus, and then plug H plus into the pH equation. Or you could find pOH, which is what I'm going to do. So if I just go ahead and take the negative log of that number, of the 0.00, I got 3968627. I'm just going to take the negative log of that. I get 2.40 technically. So that is the pOH. And then the pH, if you remember, the pH plus the pOH is equal to 14. And so all I'm going to do is just take 14 minus 2.4, and I will get the pH is equal to 11.6. And that's the pH. And that pH makes sense because it is basic, and we have a decently concentrated weak base solution. A quarter molar is certainly not the highest concentration you'll ever come across, but it's not weak by any means at all. Like it's a moderate concentration, quarter molar. And so having a moderate concentration of a moderately weak base, it makes sense to me that the pH would be around 12. Now if we got to the end here and you had forgotten that what you were finding was the pOH when you did that first calculation, you should be able to catch yourself here and say, wait a second, the pH is 2? How is the pH of a weak base solution acidic? Like that should be a blaring red flag saying wrong, wrong, wrong. You need to think about your answers, because that's a fairly common thing. I would say at least once or twice every exam. If I include a question like this, where you're doing a weak base, someone will forget that what they actually have here at the end is not the concentration of H+, it's the concentration of OH-, and they'll forget to convert from one to the other, and they'll have a very wrong pH value. All right, one last thing here about weak bases before we finish up for this video. Ka and Kb, the two dissociation constants, are actually related to each other for conjugates, and this is only true for conjugate acids and bases. So you can't take the Ka of HF and say it's related to the Kb of ammonia. Like it's not going to work. That doesn't happen. But the dissociation constant of HF and the base dissociation constant of F- are related. Because they are conjugate acid and base, the dissociation constants are related like this. So Ka times Kb is equal to Kw, and just in case you don't remember what Kw is, it's just the 1 times 10 to the negative 14. It's the dissociation, or not the dissociation, it's the equilibrium constant for the autoionization of water. 1 times 10 to the negative 14. So even if you don't know the base dissociation constant for a weak base, if you're familiar with the weak acid that it's the conjugate of, you can work out Kb using this equation, which is pretty nifty sometimes, because a lot of the time you'll find books where you have a whole table of Ka values, like a whole page worth, and then they'll have like 5 Kb values. And you're like, well, that's not terribly helpful if you're doing weak base stuff anyway. And so if you can find the conjugate on the weak acid table, then it's fairly simple to work out what the Kb is. All right, we'll finish there for this one. In the next one, we're going to talk about a few different things that affect how strong an acid or a base is. And so I will see you in that video.